How dense can matter become before space itself begins to concede, reshaping under a pressure so deep that geometry changes character and the familiar textures of reality lose definition? If explorations like this resonate with you, you're welcome to gently like the video or softly tap subscribe, only if this quiet corner of physics truly aligns with your curiosity. Matter begins loosely, built from atoms full of internal emptiness. Compression first touches these outer regions, folding electron clouds inward and tightening the structure of matter. At modest extremes, electromagnetic forces resist, maintaining the coherence of solids. Under greater compression, those forces yield, and electrons are pushed into tighter configurations. Eventually, a deeper boundary emerges. Electrons can no longer be pressed together without violating the most fundamental rules of quantum identity. Their refusal creates the support that holds a white dwarf in equilibrium, a stellar remnant containing the mass of a star within the scale of a planet. Its substance is so compact that ordinary intuition has nothing to compare it to. Increase the compression further, and even that boundary breaks. Electrons merge with protons, and neutrons dominate the structure. Neutron stars carry this state across the cosmos, compact bodies so dense that a fragment the size of a raindrop would outweigh entire mountain ranges. Their gravity curves space sharply, bending the paths of light, slowing the flow of time, and creating conditions that erase the distinctions that define everyday matter. Beyond this frontier lies a transformation even more profound. Neutrons themselves can lose their individuality. Their internal quarks, usually confined by the strong interaction, may be forced into a continuous fluid of fundamental components. In laboratory accelerators, glimpses of this state appear for moments so brief they barely count as instants. In the heart of a collapsing star, this state may endure and deepen, a relic of the earliest universe returning under pressure. Even this exotic matter cannot resist unlimited gravitational pull. Once enough mass gathers, collapse accelerates past every known barrier, and a black hole forms. Here, the idea of density becomes slippery. Classical descriptions imply an undefined concentration at the center, but modern theories suggest something subtler. What matters most is not the heart of the collapse, but the horizon surrounding it, a boundary beyond which all possible motion bends inward. Inside this boundary, pressure and curvature reach beyond the reach of normal description. The familiar continuity of space is strained toward scales so small that geometry itself becomes unstable. Various approaches to quantum gravity attempt to describe this regime. Some propose that space is built from discrete units too small to divide further. Others suggest a fundamental tension woven into the fabric of reality that resists further collapse. In these models, the universe prevents total geometric failure through its own underlying structure. Black hole entropy reveals a clue to this limit. The amount of information such an object can contain grows with its surface area rather than its internal volume. This implies that space may refuse to store unlimited complexity. Instead of allowing matter to compress beyond all meaning, spacetime reorganizes itself, encoding information on a boundary rather than forcing it deeper. The question of how dense matter can become then resolves into a layered answer. Atoms collapse inward. Electrons reach their limit. Neutrons reach theirs. Quarks momentarily resist. And beyond all material structure lies a geometric threshold where space-time itself intervenes, not with a physical barrier, but with rules that prevent the universe from crossing into impossible configurations. Density no longer describes matter. It describes the way space-time rearranges itself in the presence of overwhelming gravity. Beyond the point where matter loses all recognizable structure, a different kind of question begins to form. Instead of asking how tightly matter can be packed, the focus shifts to what it means for space-time to respond at all. The collapse of matter into a black hole is often imagined as a journey inward, but the more useful picture is outward. The horizon expanding, sealing off a region of the universe, altering the gravitational landscape for everything around it. The horizon is not a surface in the usual sense. Nothing rests on it. Nothing touches it. It is a threshold in the flow of time and motion, a place where the direction of what the universe considers forward bends inward. The physics here depends not on material density, but on the shape of space-time itself. Compression continues, but the meaning of compression changes. Inside, coordinates behave differently. Volume becomes a concept without stability. Distances lose their conventional relationship to the mass within. New questions arise at this stage, not about particles or pressure, but about the nature of information. Matter falling inward does not simply disappear. It changes what the horizon encodes. Every bit of structure, every trace of identity, contributes to the subtle modifications of that boundary. The collapse does not obliterate history. It arranges it differently, redistributing complexity across the outer geometry. The interior, though hidden from observation, becomes a region where theories diverge. Some describe a finite core where quantum effects counteract further collapse. Others propose a bridge to a separate domain of space-time. Still, others imagine a continuously shrinking but never vanishing region where geometry wavers between classical curvature and quantum discreteness. Each of these possibilities offers a different interpretation of how the universe prevents impossible density. Yet the most intriguing consequences appear not deep inside, but in the space around a massive, collapsed object. The gravitational field alters the trajectories of light, stretching pathways so that signals weaken, redden, and drift toward faintness as they approach the horizon. Even without touching the boundary, nearby space-time reflects the transformation within. Orbits tighten into unexpected shapes. Radiation skims the edge of the horizon before escaping outward, carrying with it the faint signature of events occurring near the threshold. This environment reveals something subtle. The true measure of the collapse is not the density of the material, but the curvature imposed by mass and energy. Curvature becomes the universal language, describing how paths bend, how time flows, how horizons form. In ordinary conditions, curvature is gentle, shaping planetary orbits and stellar balance. Near a collapsed object, curvature intensifies to the point where no familiar intuition holds. There are regions surrounding such an object where particles can hover in unstable equilibrium, sustained by the tension between inward gravity and outward radiation. Other regions create natural traps for light, forcing it into orbits that loop repeatedly before escaping or plunging inward. These structures arise not from matter, but from the geometry sculpted by mass. It is here that the influence of extreme density becomes visible to distant observers. The influence extends even further when a collapsed object rotates. Rotation drags space-time with it, forcing nearby regions to twist. This effect creates zones where no object can remain still relative to the distant universe, because space-time itself is in motion. Matter entering this region follows spirals shaped not by mechanical forces, but by the flow of the underlying geometry. Even the energy available to outgoing particles changes, allowing strange processes where momentum can be exchanged with the rotating geometry itself. All of this emerges from the original collapse, long after the matter inside has lost identity. In this way, the densities reached within a collapsed object have consequences that ripple outward through the universe, modifying the behavior of light, energy, and motion across vast distances. The collapse does not end by creating a sealed-off remnant. It imprints itself upon the cosmos indefinitely. At the edge of theoretical exploration lies a question even deeper than density: whether spacetime possesses an inherent limit to how much curvature it can sustain. Some models propose that curvature saturates when quantum effects intensify, preventing further distortion. Others suggest that curvature can exceed classical expectations by redistributing energy into the fabric of spacetime in unfamiliar ways. These ideas differ, but they all aim to replace the unreachable notion of infinite compression with a more coherent physical principle. Such models introduce new possibilities for the interior of a collapsed object. Instead of a point of impossible concentration, the core might become a region of finite, persistent structure, shaped by quantum geometry. In this interpretation, the densest possible state of matter is not a singular point, but a domain where the normal relationships between distance and energy no longer apply. Geometry becomes elastic, self-sustained, capable of resisting collapse through properties that do not appear under ordinary conditions. Under this view, the concept of density becomes almost secondary. The primary reality is the configuration of spacetime. Matter no longer exists as particles arranged in space. It exists as a modification of the geometry itself. The densest state is not a substance but a pattern in the fundamental structure of the universe, a configuration that cannot compress further because the underlying fabric refuses additional curvature. This idea leads to a broader perspective, that the universe contains natural limits not only to the states matter can reach, but to the states spacetime itself will allow. These limits define the boundaries of collapse, the formation of horizons, and the conditions in which new regions of spacetime may emerge. They also delineate the threshold where classical physics hands responsibility to quantum geometry, marking a place where familiar concepts dissolve into deeper, more abstract forms. This boundary, the horizon of knowledge more than the horizon of a collapsed star, is where the question of density transforms again. Instead of asking how tightly matter can be pressed, the more revealing inquiry becomes how deeply spacetime can curve while still preserving coherent structure. The answer, whatever form it ultimately takes, will describe not only the extremes of collapse, but the architecture of the universe itself. Even far from the collapsed core, the influence of extreme curvature creates domains where ordinary intuition dissolves. Waves of light stretch into deeper colors as they climb away from the gravitational field, not because anything interferes with them, but because the flow of time itself differs from place to place. This slow unwinding of frequency becomes a quiet signature of what occurred deep within, the final stages of matter losing every distinct form, leaving only the imprint of its collapse on the surrounding geometry. In regions where the gravitational field is strong but not overwhelming, particles drift into orbits that behave unlike those around stars or planets. They follow paths that turn inward, tighten, wobble, and sometimes loop upon themselves in shapes that appear impossible anywhere else in the universe. These orbits reveal that the densest states of matter do more than compress mass. They reshape the rules that guide motion, creating pockets where direction and momentum shift in ways that challenge familiar expectations. Rotation introduces an even stranger consequence. A spinning, collapsed object forces spacetime into a kind of sweeping motion, pulling nearby regions into a silent whirl. In this domain, nothing can remain still relative to the distant universe. The fabric of reality itself is carried along, twisting around the collapsed mass. Particles passing through this region gain or lose energy depending on how they move relative to the rotation, as if motion can be borrowed from the turning of space-time. This exchange hints at a deeper link between geometry and energy, one that becomes visible only under the most extreme conditions. The behavior of fields also transforms near such objects. Magnetic and electric structures that remain stable elsewhere become distorted, stretched into elongated patterns that skim the boundary of the horizon. Under certain conditions, these fields can fold into configurations that concentrate energy in unexpected ways, creating jets that stream outward at remarkable speeds. These jets draw their power not from the matter itself, but from the organized curvature surrounding it, illustrating how deeply the collapse reshapes everything within reach. Further away, where curvature is gentle enough to allow stable motion, a different story unfolds. The collapse leaves behind waves in the structure of space-time, faint ripples that travel vast distances before fading into the cosmic background. These ripples, though delicate, carry information about the moment when matter could no longer resist. They reveal the rhythm of the collapse, the rotation, the merging of structures, and the final shift into a state beyond conventional density. Even after the event has passed, these waves preserve a record of the universe rearranging itself at extreme boundaries. Yet the most intriguing possibilities arise in theories that allow spacetime to connect to new regions through the collapse. Some suggest that the core may narrow into a throat leading to a separate domain, not as a tunnel for passage, but as a geometric continuation. Under such models, the densest possible state is not merely a compressed region, but a transformation in the global structure of the cosmos. The collapse becomes an act of creation, generating a new expanse beyond the reach of the original universe. Whether such structures remain stable or collapse further into quantum foam remains an open question, but the idea underscores that density becomes a gateway rather than an endpoint. Other approaches propose that the interior of a collapsed object evolves over time in ways hidden from the outside. Even though nothing escapes the horizon, internal evolution may continue, driven by the relentless pressure and the quantum properties of spacetime. In this picture, the densest state is dynamic rather than fixed, shifting through configurations that differ profoundly from anything in ordinary matter. These transitions would remain invisible to the cosmos, identifiable only through indirect traces on the horizon or through the patterns of radiation that slowly emerge from the boundary. In all these views, a common thread appears. The densest state of matter does not behave like a traditional substance. It is not a compressed form of atoms, nor a tighter arrangement of particles, nor even a simpler collection of quarks. Instead, it is a condition where matter and geometry become indistinguishable, where the collapse shapes spacetime so thoroughly that the distinction between material density and spatial curvature no longer holds. What remains is a configuration built from the deepest rules of the universe, a state where existence itself becomes compact, concentrated, and abstract. This understanding shifts the original question into a new frame. The limit of density is not simply the point where matter can no longer compress. It is the threshold where matter ceases to be a meaningful concept. Beyond that lies a realm where geometry carries the burden of structure, where the universe enforces boundaries that prevent physical impossibilities, and where collapse transitions into a form of order that cannot be described using familiar terms. In quieter regions of the cosmos, far from horizons and catastrophic collapse, the same boundaries appear in miniature, written into the behavior of dense objects that never quite reach the brink. Neutron stars, magnetars, and other compact remnants become laboratories where the universe rehearses its limits without crossing them completely. Inside these objects, nuclei are crushed into shapes that do not occur anywhere else. The outer layers contain exotic lattices where neutrons seep between a grid of nuclear clusters, forming structures that resemble sheets, rods, and tangled networks. Physicists call this nuclear pasta, a strange intermediate between matter and field, dense enough to distort but not yet surrendered to pure curvature. Deep beneath that crust, superfluid neutrons flow with almost no resistance. Quantum effects that are fragile in ordinary materials become dominant in these extreme interiors, guiding the rotation and vibration of the entire star. When the spin of such an object suddenly shifts, the change reveals that the interior behaves like a rigid but fluid structure, storing and releasing angular momentum in abrupt events called glitches. Those tiny jerks in rotation, observed from across space, are traces of density negotiating with geometry, revealing how far matter can be pushed while still retaining some internal agency. In these stars, density does not simply describe how much mass occupies a region. It determines how the building blocks of matter rearrange themselves, which phases of nuclear matter become stable, and how the strong interaction shapes configurations that cannot form elsewhere. Theoretical models sketch phase diagrams where pressure and temperature carve out domains of different behavior, regions where nucleons are free, others where they line up into ordered patterns, still others where quark degrees of freedom start to leak through. Each point on such a diagram corresponds to a possible chapter in the collapse story, from ordinary matter to the threshold of geometric domination. The early universe passed through similar phases in reverse. In the first moments after the beginning, densities and temperatures were so high that no stable nuclei existed. The entire cosmos resembled a vast, expanding plasma, closer to the interior of a compact star than to the present quiet of interstellar space. As expansion proceeded, density fell and new forms of order emerged. Quarks confined, protons and neutrons assembled, nuclei formed, and eventually atoms appeared. The journey from formless plasma to structured matter was essentially the reverse of gravitational collapse. Instead of being driven inward by gravity, the cosmos opened outward, allowing new degrees of freedom to crystallize out of the chaos. Thinking of these two directions together, collapse and expansion, reveals a symmetry. At extremely high densities, matter and geometry entangle so thoroughly that usual categories fade. At moderate densities, matter can form complex structures, from stars to planets to living systems. At extremely low densities, geometry dominates again, spreading matter thinly across enormous volumes. The universe cycles between these regimes, shaping and reshaping the distribution of matter over cosmic time. On the theoretical frontier, some cosmological models suggest that the maximum densities reached inside collapsing regions might mirror those in an earlier cosmic epoch. Instead of a true beginning with undefined conditions, reality may oscillate or bounce, with each phase of expansion preceded by a period of contraction. In such pictures, the densest possible state is a staging point rather than an end point, a bridge between eras where spacetime compresses to its quantum limits and then re-expands in a fresh configuration. Whether this bounce is smooth or violent depends on the details of quantum gravity, but in all such scenarios, the same conclusion emerges. There exists a scale beyond which neither matter nor spacetime will tolerate further compression. Observations of gravitational waves provide an emerging probe of these extremes. When two compact objects spiral together and merge, the waves they emit encode their internal structure. A collision between black holes carries a clean geometric signature, shaped mostly by mass and spin. A merger involving neutron stars carries additional information: tidal distortions, resonant vibrations, and the moment when matter finally gives way to full collapse. Comparing different events gradually constrains how rigid neutron matter can be, how compressible it becomes near the threshold, and how the transition toward a horizon unfolds. These cosmic collisions act like experiments far more powerful than anything built on a planet. High-energy particle collisions, by contrast, explore the microphysical side of the question. When heavy nuclei are smashed together at near-light speed, the resulting fireball briefly reaches densities and temperatures reminiscent of the earliest universe. Detectors capture the spray of particles that emerges as this fireball cools and expands. Patterns in that spray reveal how quarks and gluons flow, how they interact as a nearly perfect fluid, and how they freeze into ordinary hadrons. Although the timescales are unimaginably short, the physics extracted from these experiments informs our understanding of what might occur in the cores of compact stars, or at the centers of collapsing regions. Across these different settings, a unified picture begins to take shape. There is no single number that marks the ultimate density, no fixed threshold where the universe simply breaks. Instead, there is a layered sequence of limits. Electrons resist compression until they merge into neutrons. Neutrons resist until quark degrees of freedom dominate. Quark matter resists until geometry itself is forced into radical curvature. Beyond that, quantum structure in spacetime refuses further distortion, imposing a boundary that is better described in terms of information and geometry than in terms of squeezed particles. In this sense, the densest state of matter is not a point of infinite concentration, but a regime where the rules that normally govern matter are replaced by rules that govern spacetime directly. What began as a question about packing more and more substance into a smaller and smaller region ends as a question about which configurations of reality are permitted at all. The answer lies not in the collapse of grains into a tighter pile, but in the recognition that the universe has written into its structure a refusal to permit contradictions, a quiet set of boundaries beyond which even gravity must yield to deeper principles. The notion of a final limit to compression invites a broader reflection on how the universe distributes its extremes. Regions of overwhelming curvature are rare, but their influence extends far beyond their boundaries. Even a collapsed object hidden behind a horizon reshapes galactic environments, bending the paths of stars, dictating the flow of gas, and anchoring the immense spirals that form galaxies. Density achieves a kind of paradox here. The most compact states of matter, which occupy the least space, govern the largest structures in the cosmos. In these environments, the interaction between matter and geometry becomes almost architectural. Gravity sculpts patterns in gas clouds light years across, guiding them along curved pathways shaped by a mass that can no longer be described by any conventional density. These patterns fold, twist, and shear into vibrant structures that seed the birth of new stars. Collapse at one extreme creates the conditions for creation at another, illustrating a cycle where density's limits influence the universe far beyond their origin. Closer to the horizon, the influence grows more subtle. The rotation of a collapsed object induces a frame-dragging effect that extends outward, warping the region into a shape, reminiscent of a whirlpool written into the very coordinates of spacetime. The direction of this twist cannot be opposed by any stationary motion. It is woven into the environment. Gas, spiraling inward, forms luminous disks that heat under compression and friction, shining with intensities that outmatch entire galaxies. These displays reveal the threshold conditions where gravity, rotation, and matter interact in a balancing act that remains stable only because the densest state lies sealed within. Within these disks, matter behaves with a complexity that surpasses ordinary physics. Fragments collide, ionize, and arrange into flows governed by magnetic topology as much as by gravity. Magnetic fields tangle, amplify, and reconnect, releasing bursts of radiation that illuminate these regions with flickering pulses. These emissions are not mere byproducts. They reveal the behavior of matter nearing the boundary where density ceases to describe its character. The closer matter approaches the horizon, the more its fate is governed by the subtleties of curved spacetime, rather than by anything intrinsic to the material itself. Farther out, where the influence is gentler, the universe displays signs of the densest realms in the patterns of high-energy particles traveling through interstellar space. Some of these particles carry energies that defy simple explanations, hinting at origins linked to the violent neighborhoods near collapsed objects. Their interactions with magnetic fields across cosmic distances create signature bends and arcs, like long shadows cast from invisible sources. The densest matter, hidden and inaccessible, announces its presence over vast scales by accelerating particles to velocities that challenge every other known mechanism. In addition to these energetic traces, certain stars reveal their proximity to collapsed companions through peculiar motions. A star bound to a collapsed object drifts in a way that betrays an unseen partner, one too compact to reveal itself through light. These binary systems behave like precision instruments for detecting gravity's strongest expressions. The motion of the visible star encodes the mass and spin of its hidden counterpart, allowing physicists to infer the nature of the dense core within. Through this indirect method, collapsed objects become readable even when entirely invisible. More exotic still are the scenarios where dense objects interact with each other. When two collapsed bodies orbit in close proximity, the curvature they each impose becomes entwined. Their horizons distort, stretch, and eventually merge. During this process, the geometry surrounding them vibrates, sending waves into the cosmos. These waves carry information not only about the masses involved, but about the structure of spacetime at the moment when density reached its collective limit. Each such event becomes a natural experiment, demonstrating how the universe handles compression on scales far beyond any laboratory. The waves that reach observers are astonishing in their subtlety. They arrive as faint fluctuations in distance, expanding and contracting tiny segments of space in rhythmic patterns. These rhythms reveal the internal structure of the merging bodies, whether they were rigid or fluid, whether they possessed surface layers that resisted deformation, or whether they had already crossed into the realm where matter transitions into geometry. In this way, gravitational waves become a language for deciphering density's highest thresholds, carrying messages from regions where no particle or photon can escape. Some theories propose that density's ultimate limit is not defined by matter's inability to compress, but by spacetime's refusal to shrink further. In this view, the universe embeds a minimal scale into its architecture, a smallest unit that cannot be subdivided. At this limit, distance itself loses meaning. Spacetime behaves less like a smooth continuum and more like a network of interconnected elements, each occupying a minimal piece of reality. Any attempt to compress matter beyond this scale results not in further collapse, but in a reconfiguration of spacetime that prevents inconsistency. In such models, the densest state is a kind of equilibrium between gravitational attraction and quantum structure, a balance that halts collapse without dispersing it. The region inside a collapsed object becomes a repository of curvature, energy, and information stored in a form that avoids contradictions. While this structure remains concealed behind a horizon, it stabilizes the configuration and preserves the universe's rules. No infinite compression occurs. Instead, a new regime emerges, defined not by pressure or temperature, but by the geometry of existence itself. Other models are more speculative. Some theories propose that when collapse reaches the deepest quantum scales, a form of expansion begins internally, creating an entirely separate region of spacetime disconnected from the original. In this scenario, the densest possible state is a transitional one, marking the point where the universe creates a new branch. From the viewpoint of the original universe, the collapsed region remains compact. From the viewpoint of the new region, an expansion occurs, giving rise to a fresh expanse with its own laws and structures. Whether this corresponds to a new universe or a continuation of the original remains a subject of debate. In contrast, some proposals treat the interior of a collapsed object as a region where time flows differently from the outside world. The collapse might slow, pause, or evolve along trajectories that never complete from the perspective of internal observers. In this picture, density approaches its limit asymptotically, never fully reaching the threshold that external geometry suggests. The interior becomes a region suspended between extreme curvature and quantum stability, neither collapsing completely nor reversing into expansion. This creates a delicate tension where the concept of density must be reinterpreted, since no single observer can describe the entire configuration. These diverse models share one central idea: that density is not merely about packing more matter into a smaller region. It is a measure of how deeply the universe allows itself to be curved. Matter serves as the agent that drives curvature, but the true limit lies in spacetime's own tolerance for distortion. At moderate scales, matter dictates the shape of geometry. At extreme scales, geometry dictates the fate of matter. Eventually, there comes a point where the identity of matter dissolves entirely and only curvature remains. This insight shifts the meaning of density's upper bound. Instead of representing a crushing endpoint, it becomes the threshold where matter and spacetime fully merge, where particles and fields no longer exist as separate entities, but blend into the same underlying structure. The densest state is not a physical object, but a configuration of the universe where familiar concepts lose definition and new principles take over. Through this lens, the densest possible condition is less a destination and more a transition. Collapse changes the relationship between matter and geometry until geometry alone defines the outcome. Beyond that boundary, no further compression is meaningful. What remains is a shape in the fabric of the universe, a monument not to matter's endurance but to spacetime's ability to absorb, encode, and transform everything that falls within its reach. The deepest implications of density unfold not inside the collapsed core, but in the ways the universe responds to its existence. Every region of high curvature creates patterns that spread outward, influencing the behavior of matter and radiation long after the original collapse has settled into silence. These patterns reveal how flexible spacetime can be before it reaches its ultimate limits, and how it adapts to sustain consistency even when pushed to extremes. Around collapsed objects, the bending of spacetime forms channels where energy flows in unexpected ways. Particles falling inward follow spirals shaped not by the attraction of material substance, but by the shape of the surrounding geometry. These spirals tighten and stretch, creating streams that collide and reconfigure. These collisions produce bursts of radiation that illuminate the region like flickering signals from a realm where matter nears its disappearance into pure curvature. Even beyond these luminous events, the influence of the collapsed object stretches across interstellar distances. Gas clouds drifting through a galaxy alter their trajectories in subtle arcs, responding to the presence of a mass they will never see. These arcs demonstrate that curvature extends beyond the immediate gravitational well. It becomes a quiet architect guiding the distribution of cosmic structures, sculpting the forms that galaxies eventually display. Within certain galaxies, jets of radiant material beam outward from the central region, aligned with the rotation of the collapsed core. These jets arise when magnetic fields near the horizon twist into narrow channels, forcing energetic particles into beams that extend farther than entire star systems. Their presence demonstrates that extreme density produces not only inward collapse, but outward expression, a dynamic balance between inward gravitational pull and outward electromagnetic structure. The influence of dense matter also appears in the phenomenon of tidal disruption. When a star ventures too close to a collapsed object, the difference in gravitational pull between its near and far sides becomes overwhelming. The star elongates, breaks apart, and forms a luminous ring that spirals toward the horizon. This destruction reveals the tremendous gradients in curvature that surround the densest realms. The star is not crushed by contact, but torn apart by uneven stress across its structure, a testament to the strength of geometric forces near the limit. Yet, even more interesting are the regions where matter manages to resist total collapse for extended periods, hovering near the horizon without crossing it. Radiation pressure, magnetic fields, and angular momentum conspire to hold material in precarious equilibrium. These suspended shells behave like shifting atmospheres, glowing with heat and emitting patterns of light that mark the boundary between the observable universe and the region from which nothing returns. The study of these transient layers offers insight into how the universe approaches its densest states without fully committing to them. Inside the horizon, the evolution of the collapsed core unfolds under conditions that challenge every known framework. The behavior of time becomes directionally constrained, guiding everything toward deeper curvature. The interior no longer contains static locations. Instead, it is a region where movement and destination merge. Matter, having lost its identity, flows into configurations that depend solely on the structure of spacetime. Its compression is no longer opposed by any physical force. The only remaining counterbalance comes from quantum geometry, which imposes limits that classical descriptions cannot reflect. Speculations about the interior envision a region where space-time becomes foamy, riddled with fluctuations that prevent the formation of an infinitely compressed point. These fluctuations may act like a spring, resisting collapse at the smallest scales. They might also create internal boundaries where curvature cannot grow further. Such boundaries could resemble membranes or shells, formed not from particles but from the tension inherent in the quantum structure of reality. These structures, though invisible to the outside universe, determine how collapse reaches equilibrium. Another line of thought suggests that the interior forms channels of geometry that lead to new regions. These channels might pinch off, forming isolated pockets cut from the original cosmos. In this scenario, density's ultimate limit becomes the seed of a new expansion, a birthplace for another domain that grows independently. From the perspective of the original universe, this transformation remains hidden behind the horizon. From the internal viewpoint, a new cosmos emerges, free from the collapse that created it. Whether these internal expansions stabilize or fracture into smaller regions remains an open question. Some theories envision the interior as layered, with each layer representing a distinct regime of curvature. These layers might hold different types of geometric structure, each tolerant of a particular range of density. As collapse deepens, the interior transitions from one layer to another, shifting the rules governing motion and energy. At the deepest layer, density ceases to be meaningful. Nothing can be packed further, because distance itself cannot be made smaller. Instead, matter becomes indistinguishable from the geometry that contains it. Outside the horizon, the world continues to evolve in response to the presence of the collapsed object. Stars drift through orbital paths altered by curvature. Gas funnels toward the center, feeding the collapsed mass over long periods. Entire galaxies reorganize themselves around the influence of a core that contains no recognizable matter. The densest regions, though hidden, guide the formation of structures on a scale that dwarfs them. Collapse becomes a shaping force for everything surrounding it. Over time, even collapsed objects change. They emit radiation through quantum processes occurring near the horizon, gradually losing mass. This emission is faint, almost imperceptible, but persistent. Through this mechanism, the densest state of matter slowly transforms into radiation, returning its content to the universe over vast timescales. The horizon shrinks, the interior reconfigures, and the once formidable core eventually dissolves into energy. Density, once unthinkably high, reduces to nothing more than the gentle whisper of radiation drifting into the cosmic background. The eventual fading of collapsed objects suggests that density is transient, even at its maximum. The universe does not allow the densest configurations to remain eternal. Over enormous spans of time, curvature softens, horizons contract, and the geometry that once imprisoned matter releases it back into the cosmos. The cycle of collapse and evaporation reveals a profound symmetry. The densest states and the most diffuse states are connected by processes that unfold over cosmic ages. This evaporation process raises deeper questions. If the densest object dissolves, what becomes of the information encoded on its horizon? Some theories propose that this information is gradually released along with the radiation, encoded in subtle correlations. Others suggest that information persists in a modified form, stored in the geometry itself even after the object disappears. Still, others envision a more radical idea, that information becomes woven into the expanding fabric of the universe, diffused so thoroughly that it cannot be recovered but also not truly lost. These considerations push the question of density into the realm of information theory. Instead of describing how compact matter can become, one begins to ask how much information can be stored in a given region of space and how this information behaves under collapse and evaporation. The densest possible configuration may not be defined by mass but by the capacity of spacetime to encode structure before its geometry must shift to avoid contradiction. In this formulation, density becomes a property of information rather than of matter, a shift that reframes the entire discussion. The notion that information governs the limits of density connects collapse to quantum mechanics more deeply. Quantum fields, by their nature, carry information even in empty space. The collapse of matter reorganizes these fields, altering their correlations across the horizon. The stability of the collapsed object depends not only on energy but on the coherence of these correlations. At the densest limit, information itself enforces constraints that prevent impossible configurations. This perspective also links density to entanglement. The horizon may be thought of as a surface where entangled pairs of states separate, with one partner falling inward while the other remains just outside. These pairs contribute to radiation, to the gradual release of mass, and to the preservation of information. The densest state becomes a boundary where entanglement dictates the behavior of energy and geometry, weaving together concepts once treated as separate. Even more speculative ideas propose that the densest state is not confined to collapsed objects alone. The vacuum of space, according to some interpretations, contains latent energy and structure that mirrors the conditions inside collapsed regions, albeit in a diluted form. Under certain circumstances, this vacuum might momentarily manifest dense configurations without collapse, creating transient pockets where geometry folds briefly before returning to equilibrium. These fleeting events suggest that density is not always tied to mass, but can emerge from the geometry alone. If such events occur, they offer a glimpse into the nature of density not as a state of matter, but as a state of spacetime. In this view, the ultimate limit does not require enormous mass. It requires conditions that allow geometry to tighten into extreme curvature. These conditions could arise from fluctuations in the vacuum, from rare alignments of energy fields, or from processes that remain unknown. They would be brief, tiny, and difficult to detect, yet profoundly informative about the universe's behavior at the smallest scales. Overarching all these ideas is a central realization. Density's limit is not an endpoint, but a boundary that guides the evolution of cosmic structure. It tells matter how far it may go before geometry intervenes. It tells geometry how much curvature it can sustain before quantum rules assert themselves. It tells information how deeply it can be encoded before surfaces rather than volumes must carry the record. The universe expresses this boundary in every collapsed object, every gravitational ripple, every orbit shaped by hidden mass, and every quantum fluctuation that hints at a deeper architecture. The densest possible state is the crossroads where matter, geometry, information, and quantum structure converge. It is the horizon of meaning itself, the place where familiar categories dissolve and new principles decide what the universe permits. The strange subtlety of density's upper boundary becomes clearer when considering that the universe behaves differently, depending on how close one approaches that boundary. In regions where density remains well below the threshold, spacetime behaves cooperatively. Distances remain stable, motion follows smooth curves, and energy distributes itself across fields in predictable ways. Matter clumps into stars and planets. Gas clouds migrate along gravitational gradients, and galaxies carve out majestic spirals governed by orderly dynamics. But with each incremental rise in compression, gravity and quantum mechanics begin to negotiate more assertively, bending the rules that ordinarily guide structure. There are transitional regimes where matter takes on forms that do not fit neatly into any category. In the interior of compact stars, for example, particles become arranged into patterns bearing more resemblance to textures than to discrete objects. These textures arise because nuclear forces cannot decide whether to bind or separate clusters of nucleons. Instead, they settle on shapes that occupy a middle ground. Webs and sheets intertwined with superfluid components flowing through their gaps. This mixture of rigidity and fluidity reveals that density reshapes not just matter's form but its function, altering how it transmits stress, supports rotation, and stores energy. Even deeper in these stars, the nature of motion changes. Instead of individual particles carrying angular momentum, entire regions of superfluid sweep through the interior without friction. These motions slip and shift, occasionally locking against the inner lattice before releasing abruptly. When such a release occurs, the star's rotation can change in an instant, broadcasting a faint signal across space. This sudden shift hints that density prepares matter for states where ordinary inertia dissolves into collective behavior, governed by quantum rules that dominate at scales typically associated with macroscopic objects. Meanwhile, the universe incorporates these dense remnants into a larger cosmic tapestry. Gas clouds drifting in from interstellar space interact with their gravitational influence, compressing into structures that can ignite into new stars. In this sense, density not only marks the end of stellar evolution, but seeds the beginning of new cycles. The densest states become anchors around which galaxies organize themselves, each collapsed core acting as a sculptor guiding the motion of entire star systems. Within the dense accretion flows surrounding collapsed objects. Matter experiences forces unmatched elsewhere. Friction and magnetic tension combine to heat the material, stripping particles of their outer layers and sending radiation outward in complex, turbulent patterns. These emissions vary with time, sometimes rising in sharp flares when magnetic fields reconnect in violent realignments, sometimes dropping into quiet intervals where the inward flow becomes smoother. This variability encodes the intricate dialogue between in-falling matter and the geometry beneath it, each shift revealing another facet of how density shapes the environment around it. Some of the most astonishing displays occur in regions where magnetic fields direct energetic particles outward in narrow streams. These streams can extend across distances that dwarf any physical object, maintaining tight collimation over scales that challenge standard explanations. Their stability arises from the interaction of rotation, magnetic tension, and the curvature of spacetime itself. In these jets, density announces itself in the form of motion, accelerating matter to extraordinary speeds and carving luminous lines through intergalactic darkness. The real complexity unfolds at the boundary where matter approaches the horizon. Radiation tries to escape but becomes stretched, dragging its frequency downward as it attempts to climb away from the gravitational slope. Particles hover in unstable balance, torn between outward momentum and inward curvature. Some manage to escape, carrying with them information about the conditions they encountered. Others linger, circling the horizon in paths that require exquisite precision. These delicate orbits can persist for short spans before spiraling inward, leaving behind traces in the pattern of emitted radiation. Further out, the influence of these extreme regions propagates through gravitational waves, spreading distortions in spacetime across cosmic expanses. These waves arise not only from violent mergers, but also from subtle oscillations in the structure of dense objects, each vibration imprinting a signature on the surrounding geometry. Detecting these faint ripples provides insight into how matter behaves at densities unreachable in any terrestrial environment, revealing stiffness, elasticity, and hidden phases of nuclear material. The universe also reveals density's influence through interactions between collapsed objects and their stellar companions. When a star transfers material toward a dense partner, the inflow forms spirals that tighten as they near the horizon. These spirals may break into clumps, form shock waves, or heat into incandescent rings. The behavior depends on the star's composition, rotation, and the geometry of the companion. Each system becomes a natural experiment, testing how matter behaves under the relentless pull of extreme curvature. The question of what ultimately halts collapse remains central to the study of density. If the universe contains a minimum scale of distance, collapse cannot exceed that limit. Instead, the region inside the horizon would reach a stable configuration in which geometry becomes saturated. Beyond this saturation, no further compression is possible, because spacetime can no longer sustain meaningfully smaller intervals. This scenario transforms the interior into a domain where space acquires a discrete character, composed of indivisible units connected in patterns that reflect the total mass and energy within. In such a model, density stops being a measure of mass per volume, because volume itself cannot shrink indefinitely. Instead, the densest possible state becomes a configuration where every available quantum of space is filled to capacity, like a mosaic of minimal tiles arranged in a structure determined by gravitational collapse. These tiles might warp, twist, or stretch under pressure, but they cannot reduce their size. The geometry is full. Other theories suggest a more dynamic equilibrium. Rather than settling into a fixed configuration, the interior might undergo ongoing evolution, continually adjusting to changes in curvature and quantum structure. This evolution would occur behind the horizon, invisible to the external universe but crucial for understanding how density behaves at its limit. Under these theories, the interior resembles a system searching for stability, but never fully finding it, oscillating between configurations dictated by deep quantum rules. Some researchers speculate about internal horizons nested within the exterior one. These internal boundaries might separate different phases of geometry, each with its own rules. The outer horizon isolates the interior from the universe at large, while inner horizons could isolate regions where geometry transitions from one regime to another. Between these boundaries, matter and curvature evolve along pathways that challenge the idea of density as a simple, monotonic quantity. Beyond these theoretical frameworks lies another possibility: that spacetime might tear under sufficient strain. If curvature becomes too intense, the continuity of the manifold could break, forming defects that restructure the interior entirely. These defects might resemble tears, folds, or bifurcations in the underlying fabric. Such events would not violate physical laws, but represent a profound shift in how geometry arranges itself when pushed beyond familiar limits. In this picture, the densest possible state is not a smooth, compact region, but a fractured configuration where space reorganizes itself to preserve consistency. Speculations even extend to scenarios where collapsed objects act as catalysts for entirely new regions of spacetime. Under certain conditions, the intense curvature at the core might seed a separate expansion. This expansion would be hidden from the outside universe, insulated by the horizon. Inside, distances would grow instead of shrink, creating an environment entirely unlike the collapsing region that birthed it. This idea connects density's ultimate limit with cosmic origins, proposing that collapse and creation are two aspects of a larger, cyclical relationship. The universe already hints at cycles in the manner it distributes density across cosmic history. In its earliest moments, the cosmos occupied a state of extraordinary compression, though not one that reached the impossibilities associated with classical collapse. From that initial density, expansion unfolded, lowering curvature and allowing matter to form structured systems. Over time, gravity gathered that matter into stars, which themselves underwent cycles of fusion, expansion, and collapse. Some of those collapses led to dense remnants. Others continued into the formation of horizons. In these processes, dense states are both endpoints and beginnings, key steps that balance creation and destruction. Examining the role of density across cosmic time suggests that the universe avoids extremes by transforming them. High density leads to collapse. Collapse leads to horizons. Horizons gradually evaporate. Evaporation distributes energy, and the cycle continues. Each phase enforces limits that prevent runaway processes. Density cannot exceed the structural limits of spacetime, just as expansion cannot outrun the influence of gravity forever. The universe adopts a rhythm in which compression and release balance each other, creating a cosmos that evolves without ever allowing contradictions to arise. In contemplating the highest densities, the distinction between matter and geometry fades. What begins as a question about packing atoms evolves into a question about how the universe enforces logical consistency. Dense states become expressions of underlying principles, not of material substance. They reveal that reality rests on a foundation in which geometry, energy, and information intertwine too deeply to separate. The densest possible state, then, is not a physical form but a point of convergence where these threads merge completely, shaping a configuration that neither compresses further nor fractures into impossibility. The horizon surrounding a collapsed region serves not only as a boundary, but as a filter through which the universe communicates its limits. It reflects the structure within without revealing it directly, preserving the deep secrecy of the densest states. Particles skimming the edge undergo transformations that hint at the laws operating at the threshold. Trajectories curve unpredictably, polarization patterns twist, and radiation emerging from turbulent flows arranges itself into signatures that carry the imprint of internal geometry. These faint patterns offer glimpses into conditions that cannot be probed by direct inspection. The region just outside the horizon becomes an arena where the universe negotiates between classical and quantum behavior. Fields fluctuate, sometimes creating pairs of particles near the boundary. One particle escapes, its partner is drawn inward. Through this subtle mechanism, the collapsed object loses energy over immense spans of time. Each departure in the stream of outgoing quanta marks a tiny shift in the horizon, like a tide retreating grain by grain. Although imperceptibly slow on ordinary timescales, this retreat reshapes the long-term fate of even the most massive collapsed regions. As the horizon changes, so does its influence. The surrounding spacetime, once tightly curved, begins to soften. Orbits drift, pathways straighten, and the gravitational reach weakens. The environment that once carried dramatic distortions gradually becomes gentler. Tiny variations in curvature propagate outward, traveling through the cosmic web and subtly altering the procession of structures across the universe. These shifts illustrate that the densest states are not fixed monoliths, but evolving architectures, sculpting and reshaping the cosmos through time. Inside the horizon, evolution continues in ways that defy direct observation. Some theories propose that inner regions experience a time differently, unfolding along trajectories inaccessible to the universe outside. Under such conditions, collapse becomes a process without a clear endpoint, guided by rules unfamiliar to low-density environments. The inner geometry may shift through a sequence of configurations, each shaped by both quantum constraints and gravitational imperatives. Boundaries between these configurations might carry tension, create oscillations, or produce internal horizons that separate phases of extreme curvature. There are ideas in which the interior becomes a labyrinth of geometric structures, each one balancing different aspects of curvature. Some structures might resemble expanding pockets, others contracting folds, each stabilized by quantum effects that maintain coherence. In these models, density is not uniform. Instead, it varies across this hidden landscape, forming gradients and plateaus where spacetime accommodates stress in different ways. The variation suggests that the densest possible state may not be a single configuration, but a family of states, each arising under different conditions. In contrast, some frameworks treat the horizon as a dynamic membrane, a surface whose internal degrees of freedom encode everything that fell inside. This perspective dissolves the interior entirely, reducing the problem of density to a problem of information geometry. The densest state becomes a boundary phenomenon, a limit on how much structure the universe allows to accumulate on a surface before it must shift or release energy. In this picture, the interior is not a physical space, but a representation of information content reorganized into boundary states. These boundary states evolve, radiate, and eventually evaporate, returning their information to the cosmos in a form that respects fundamental symmetries. The connection between density and information also appears in quantum field theory, where vacuum fluctuations respond to the presence of curvature. Near a horizon, the vacuum reorganizes, aligning its modes in patterns that differ from those in empty space. These alignments create measurable effects, altering how fields propagate and how particles manifest. The vacuum becomes a participant in the drama of collapse, shaping and being shaped by the extreme conditions. This profound interplay blurs the distinction between matter and the fabric of spacetime itself. portraying the densest state as one where both merge seamlessly. Another intriguing consideration is the role of entropy in determining density's upper bounds. Entropy measures the number of possible configurations consistent with a system's macroscopic properties. In regions of extreme curvature, entropy reaches levels that cannot be explained by simple arrangements of particles. Instead, entropy becomes tied to geometric properties, suggesting that the densest possible state is one where the universe maximizes informational capacity while maintaining consistency. Beyond that, further compression would violate this balance, so the geometry shifts to prevent it. Such ideas invite speculation about whether collapse might serve as a mechanism for encoding and preserving cosmic history. If information is conserved across collapse and evaporation, then the densest states become repositories of countless stellar narratives, each transformed into geometric and quantum patterns. Over cosmic timescales, these patterns would re-emerge as faint radiation, diffused through space but still carrying the subtle imprint of the histories they once represented. Density thus becomes not only a physical limit, but a custodian of memory. The influence of collapsed regions extends to the cosmic background itself. Tiny irregularities imprinted on this background may reflect ancient encounters between dense objects and surrounding matter, leaving faint marks on the distribution of energy. These marks persist over incomprehensible durations, long after the collapsed objects have evaporated or transformed. Studying these remnants helps reveal how density shaped the early universe and how its extremes guided the formation of large-scale structures. In certain models of cosmology, the universe is filled with an array of collapsed remnants scattered throughout the cosmic web. Some are massive. Others are relics of early collapse events that formed before galaxies existed. These relics contribute to the gravitational scaffolding that organizes clusters and filaments. They interact only through curvature, yet their combined influence shapes the cosmic architecture. Density, even when hidden behind horizons, becomes a quiet builder of structure, guiding matter into patterns that extend across billions of light years. As observers refine their measurements of gravitational waves and electromagnetic signals, they uncover increasingly subtle features of dense objects. Minute deviations in the frequency of ripples from collisions reveal details about the rigidity of exotic matter. Slight distortions in electromagnetic emissions uncover the presence of magnetic interactions near the threshold of collapse. These advancements hint at the possibility of probing interior conditions indirectly, unlocking new layers of understanding about the ultimate limits of density. Theoretical exploration continues to push the boundaries further. Some propose that spacetime possesses a minimal granular structure that resists being compressed beyond a certain point. Others suggest that geometry can reconstruct itself under collapse, forming structures that preserve continuity without allowing traditional singularities. There are even ideas in which spacetime behaves like a fluid, capable of flowing, curling, and reorganizing under extreme conditions, avoiding contradictions by redistributing curvature across its surface. If spacetime does possess such flexibility, then the densest states represent moments where the universe transitions from one phase of geometry to another. Just as matter shifts from gas to liquid to solid under varying pressures and temperatures, geometry might shift from smooth continuum to discrete network to quantum foam under escalating curvature. Each phase would carry different rules, and the transitions between them would define the boundary of density's reach. In this sense, The densest state becomes a phase transition in the fabric of reality. Across these theoretical landscapes, one idea stands firm. There exists a limit to how deeply matter can sink into curvature before the universe intervenes. The specific mechanism remains uncertain, but the principle is universal. The laws governing motion, information, and geometry converge to prevent a collapse that would violate fundamental consistency. Whether this limit manifests as a discrete minimum length, a maximum curvature, a bound on information, or a transformation into new spacetime regions, the conclusion remains the same. Infinite density does not occur. Instead, collapsed objects settle into configurations where geometry and quantum structure balance perfectly. Their horizons mark the threshold of this balance, separating the region where curvature can still be sensed from the region where it becomes absolute. This separation creates an environment where density reaches its deepest expression while still obeying the universe's logic. Beyond this threshold, matter and geometry cease to be distinct. The significance of this boundary extends beyond gravitational collapse. It shapes how physicists understand the origins of the universe, the behavior of high-energy fields, and the architecture of quantum gravity. It hints that reality is stitched together by principles more fundamental than matter or energy, principles that preserve coherence even as the universe explores its most extreme conditions. These principles reveal themselves not only in cosmic phenomena, but also in the subtle behavior of vacuum fields, the distribution of entropy, and the constraints on information flow. Density becomes a bridge linking these concepts, a way of understanding how the universe manages its extremes without collapsing into paradox. It is not merely a physical quantity, but a fundamental aspect of the architecture governing existence. As collapse pushes matter into deeper and deeper configurations, the universe responds with geometric transformations, quantum effects, and informational constraints that together define a maximum. This limit is not a wall, but a turning point. It marks the transition from matter to geometry, from the particles to spacetime, from physical compression to the deeper logic of the cosmos. In the vast cosmic landscape, the densest states become rare beacons of this deeper logic. They serve as demonstrations of the universe's refusal to permit impossibility, its insistence on maintaining harmony between gravity, quantum mechanics, and information. They reveal the quiet resilience of space-time, its ability to absorb extraordinary stress without relinquishing coherence. For all their secrecy, collapsed regions are among the universe's most eloquent storytellers. They express, through curvature, radiation, and distant influence, the profound laws that set the boundaries for all existence. Their horizons mark the place where density completes its journey, where matter yields to geometry, and where the universe expresses its deepest truths through silence. The universe reveals its deepest boundaries, not only through the collapse of stars, but through the subtle behavior of fields that saturate every region of space. Even in perfect darkness, fields ripple faintly, carrying the seeds of fluctuations that can grow under the right conditions. These fluctuations provide hints that the densest possible state is not an isolated phenomenon, but part of a broader spectrum of behaviors where geometry can condense into exceptionally tight configurations, even without enormous masses present. Consider a region where two fields overlap and interfere. The interference may create pockets where energy momentarily concentrates. Most of these pockets dissolve almost instantly, but occasionally one persists long enough to distort the surrounding geometry. This distortion remains tiny on human scales, yet it signals that density can appear anywhere if the right alignment of fields arises. In this sense, density is a potential woven through the vacuum, a possibility the universe can access spontaneously when fluctuations intensify. These rare fluctuations cannot collapse into stable, dense states because they lack the mass needed to sustain curvature. Instead, they flicker, test the limits, and then dissolve back into the ambient vacuum. But their behavior suggests that spacetime has inherent channels through which extreme curvature can momentarily manifest. These ephemeral events, invisible to ordinary observation, reveal that the densest conditions are not exclusive to catastrophic collapse, but emerge naturally from the quantum architecture underlying space. In regions flooded with radiation rather than mass, density expresses itself differently. Radiation carries momentum and pressure, shaping spacetime in ways distinct from matter. When radiation gathers into intense beams, it can twist and fold the geometry through which it travels. In extraordinary circumstances, beams can collide, forming intersections dense enough to momentarily resemble the conditions near a collapsed object. These intersections are fleeting, yet they illustrate that density is not purely the domain of heavy objects. It is a quality that arises whenever energy compresses into tight configurations. This interplay between geometry and energy becomes especially vivid in regions where multiple gravitational sources converge. The curvature from each source overlaps, creating interference patterns in spacetime itself. These patterns may contain saddle points, ridges, and valleys where curvature focuses or disperses. Matter passing through such regions experiences forces unlike those produced by any single mass. These combined curvatures mimic the behavior of denser states, forming a landscape where gravitational potential can sharpen suddenly, revealing how sensitively spacetime responds to the distribution of matter and energy. On even larger scales, the densest states influence the expansion of the universe. Although they occupy minuscule volumes, their collective presence, scattered across cosmic distances, subtly modifies the rate at which galaxies separate. Curvature from each dense region accumulates into a faint imprint on the overall geometry of the cosmos. Though minute, this imprint affects the balance between attraction and expansion, contributing to the delicate equilibrium that shapes cosmic evolution. In this way, the densest states function like anchors set deep within the structure of space, preventing certain runaway behaviors while allowing others. Cosmological theories exploring the earliest moments of existence suggest that density may once have approached the limits imposed by quantum geometry across the entire cosmos. During this epoch, space itself behaved differently. Fields fluctuated violently, distances contracted and expanded rapidly, and geometry changed forms with little prompting. This early era set the initial conditions from which all structure emerged. Its behavior indicates that high density is not merely a condition reached in rare stellar collapses, but a fundamental part of the universe's developmental history. From this perspective, the densest states we observe today are echoes of an era when the cosmos was suffused with conditions approaching the maximum curvature spacetime will tolerate. The collapse of stars, the formation of horizons, and the emergence of compact remnants represent localized reenactments of processes that once governed the entire universe. They are reminders of a past where density's limit shaped everything, from the smallest fluctuations to the grand scale of expansion. The geometry inside a collapsed object though hidden, may preserve aspects of this early cosmic behavior. Internal regions may contain fluctuations reminiscent of primordial conditions, either frozen into the fabric or continually resurfacing as collapse pushes geometry toward its limit. If so, the densest states become repositories not only of matter but of ancient cosmological patterns. Their interiors may hold configurations akin to memories, geometric relics of the universe's earliest chapters. Some speculative models propose that these relic patterns might influence the universe long after the collapsed region has evaporated. As radiation escapes the horizon, it may carry subtle correlations reflecting internal geometry. These correlations, however faint, could imprint themselves on the cosmic background, contributing to the mosaic of fluctuations that permeate the universe. In this interpretation, the densest states act as transmitters of deep cosmological history, subtly shaping the evolution of structures long after their disappearance. In the realm of quantum gravity, there is ongoing debate about whether spacetime should be treated as a continuous manifold or as a combinatorial structure made of finite units. If the latter is true, then collapse highlights the point where these units reach saturation. When every available unit becomes filled with energy or curvature, no further compression is possible. The geometry is full, not in the sense of matter occupying volume, but in the sense of constraints reaching their maximum. The densest state becomes a combinatorial endpoint, the completion of a pattern that cannot expand inward or contract outward without violating the underlying rules. This notion carries profound implications for the nature of mass itself. Mass might not be an independent property, but a reflection of how matter curves spacetime. When matter reaches the densest possible state, curvature no longer depends on matter in the usual sense. Instead, mass becomes encoded in the configuration of geometry. The interior no longer contains particles or fields in the traditional sense, only the curved structure that replaces them. In this regime, the distinction between mass and space evaporates. Another frontier of inquiry explores the possibility that density is not uniformly distributed inside collapsed objects, but arranged into layers separated by transition surfaces. These surfaces act as interfaces where the behavior of fields changes abruptly. Between layers, spacetime may support different symmetry states, each with unique properties. The collapse process could force transitions between these states, creating a stratified interior. Such stratification would mean that even within a collapsed object, there exist multiple densities, each governed by different geometric principles. The existence of these layers would profoundly affect how the collapsed object evolves. As radiation slowly escapes and the horizon shrinks, the internal surfaces might shift, merge, or vanish. The interior would rearrange itself, perhaps passing through configurations that resemble earlier stages of the collapse. These internal transformations would never be observed directly, but their influence on the horizon might alter the radiation's properties, allowing careful observers to infer the behavior of layers hidden inside. Some theories extend this layering concept further, proposing that the densest state involves a core where geometry becomes topologically distinct from the surrounding region. In this scenario, the interior might not share the same dimensionality as the external universe. It could fold into extra dimensions, compress into a lower dimensional manifold, or expand into a configuration where distance loses its ordinary meaning. These topological changes would reflect the universe's attempt to avoid infinite compression by altering the structure of space itself. An even more imaginative possibility is that collapse does not end in a single core, but leads to a branching structure. Inside the horizon, space-time might split into multiple paths, each representing a different resolution of quantum uncertainty. These branches could coexist without interacting, forming a complex internal architecture. In this picture, density reaches a maximum where all branches converge, creating a nexus where geometry becomes intensely constrained before diverging again. Such a configuration would represent the densest possible convergence of possibilities, a point where the universe focuses its complexity before dispersing it into a branching landscape. The study of wave behavior near horizons provides another avenue for understanding density's ultimate limit. Waves traveling near a horizon experience intense stretching and shifting. Some waves circle repeatedly before escaping, tracing out patterns that resonate with the internal structure. These resonances act like echoes, revealing details about the configuration inside. Carefully analyzing them may allow physicists to reconstruct aspects of internal geometry without ever violating the boundary. This form of gravitational holography suggests that the densest states broadcast their structure indirectly, encoded in the vibrations of space-time. The presence of these echoes implies that even the densest objects retain a form of communication with the universe. Although no particle can escape the horizon, geometry transmits subtle signals outward. These signals do not carry information in the classical sense but represent the allowed patterns of space-time vibration. Through them, the universe discloses the behavior of matter driven to the brink of its existence. As theoretical physics advances, the concept of density becomes increasingly entwined with ideas about emergence. Matter emerges from fields. Fields emerge from geometry, and geometry itself may emerge from even deeper structures that lie beneath space-time. If this is true, then collapse becomes a journey inward through layers of emergence. Density increases until matter dissolves into fields. Fields dissolve into geometry, and geometry reveals its own substructure. Each step brings the universe closer to its most fundamental description, where density is no longer meaningful in ordinary terms. At that fundamental level, the densest state may represent a configuration where the underlying constituents of spacetime reach their maximal packing, not physically but logically. Every possible relationship between these constituents becomes realized, leaving no room for further interaction without violating the rules that define them. The collapsed object becomes a statement of finality, not because matter has reached infinite compression, but because every available configuration in the foundational network has been exhausted. It is a saturation of relational possibilities. This saturation transforms our understanding of collapse. Rather than thinking of density as a monotonic squeezing of matter, it becomes the alignment of geometric relationships toward a complete expression. Once this expression is reached, the interior cannot change without affecting the horizon, and the horizon cannot shift without releasing information and energy. Over time, this release dissolves the configuration back into the general structure of the universe, dispersing the saturated relationships into more flexible forms. Seen this way, density's limit is not a catastrophic boundary, but a natural endpoint of a process that guides matter into the most concentrated state permitted by the universe's architecture. It reflects the harmony between quantum rules, gravitational dynamics, and information structure. At the boundary, the universe enforces a balance, ensuring that compression never becomes contradiction. The idea that density reaches a logical, not physical, endpoint invites another question. What happens when the universe itself approaches configurations that strain these boundaries collectively? Though dense objects are local phenomena, there are cosmic epochs where conditions across enormous regions resemble the prelude to collapse. In those eras, matter gathers in filaments so massive that the surrounding geometry arches under their influence, forming corridors where distance distorts and motion follows curves, set by an unseen tension running through the cosmic web. In such regions, the distribution of galaxies reveals how density shapes the entire structure of the universe. Clusters form at the nodes of filaments, drawn together by the combined curvature of countless masses spread across vast distances. These clusters are some of the most massive structures known, yet they display an internal organization suggesting that density has influenced their formation from the earliest moments. Within them, galaxies drift under gravitational pulls, enhanced by the presence of dense remnants, each contributing a subtle warp to the collective geometry. The motion of galaxies within these clusters is not random. Their paths curve along invisible contours sculpted by countless collapsed objects buried within the cluster's core. Every such object contributes a point of concentrated curvature, and together they create a landscape through which galaxies glide like particles moving over a multi-valued surface. These motions reveal that even without direct observation of the densest states, their influence shapes the environment on immense scales. Streams of gas flowing into cluster cores often collide at high speeds, creating shock fronts where temperatures and pressures soar. These shocks compress the gas further, triggering star formation and feeding central objects with renewed infall. In this dynamic environment, fragments torn from stars may drift toward collapsed remnants that have already consumed generations of predecessors. Each new encounter adds another layer to the curvature, another whisper of information encoded on the horizon. While the densest cores remain inaccessible, the halos surrounding them become canvases on which the universe inscribes the broader story of collapse. These halos are immense reservoirs of dark matter, ordinary matter, and radiation shaped by the gravitational influence of collapsed remnants. The distribution of material within these halos reflects a balance between inward collapse and outward pressure from various sources. This balance determines how matter arranges itself around the densest states and how the geometry accommodates these arrangements. Within the halos, turbulence reigns. Gas swirls, eddies form. Vortices collide and merge. These chaotic motions carry energy through the medium, dissipating slowly into radiation as they decay. Turbulence reveals the hidden influence of curvature, showing how density can generate order and disorder simultaneously. Even though no individual motion reveals the central collapsed object directly, the collective behavior of the halo reflects its presence unmistakably. Further away, where the pull of clusters weakens, filaments stretch across intergalactic voids, forming bridges that connect distant regions. These filaments arise from the interplay of expansion and collapse, tension and flow. They trace the regions where matter has gathered most effectively, and those gatherings owe their shape to countless episodes of compression, collapse, and stabilization at the density limit. These threads are reminders that the densest states are responsible for organizing the universe into its familiar, large-scale form. Beyond this structure lies the cosmic horizon, the boundary marking the furthest region of the observable universe. Even this vast boundary is shaped by the influence of density. The rate at which galaxies recede from view depends on how curvature has evolved over cosmic time, and curvature itself reflects the distribution of matter in all its forms, from diffuse gas to collapsed remnants. In this sense, the densest states exert influence up to the very limits of what can be observed. The cosmic horizon also reflects the subtle decay of collapsed objects. Radiation emitted over ancient spans of time eventually contributes to the overall energy density of the cosmos, altering the rate at which expansion accelerates or decelerates. Although each individual contribution is faint, the combined effect of countless collapsed remnants across cosmic history shapes the fate of the universe as a whole. The densest states, ephemeral on cosmic scales, collectively influence the universe's long-term trajectory. In regions where the density of matter drops to near vacuum levels, spacetime stretches with increasing uniformity. Yet even here, density plays a role in determining the behavior of fields and particles. Quantum fluctuations in empty space can generate virtual pairs that appear and vanish quickly, but their behavior depends on the curvature of the background. In nearly flat regions, fluctuations behave differently from those near collapsed cores. This sensitivity reveals that density's limit is not just a boundary for matter, but a boundary for the behavior of the vacuum itself. The vacuum adapts to curvature in subtle ways, adjusting the spectrum of fluctuations that define its character. When curvature is intense, the vacuum shifts into configurations that reflect the underlying geometry. These shifts influence how particles propagate, how fields accumulate phase, and how energy distributes itself across the region. In this way, density and vacuum structure interact, shaping each other in a continuous feedback loop. The densest states push the vacuum to its extremes, revealing how flexible or rigid the underlying quantum structure truly is. This interplay invites the question of whether the vacuum could itself reach a saturated state, a condition where fluctuations can no longer respond to further increases in curvature. If such a state exists, it would mark a deeper limit than any imposed by matter. The densest possible configuration would not be defined by collapsed cores, but by a universal ceiling beyond which the vacuum cannot compress its own structure. In that scenario, collapse would end not because geometry refuses to shrink, but because the vacuum's foundation cannot support any further distortion. Some quantum gravity proposals conceptualize the vacuum as a dynamic network of interacting nodes. These nodes represent minimal units of spacetime, each with constraints on how they connect to others. In this view, curvature arises from the way the network arranges itself. When collapse pushes the network toward a configuration with too many connections in too small a region, the network resists by reconfiguring itself. The densest state becomes a structural pattern of the network, where every connection reaches its maximum allowed tension. No further tightening is possible. The network is complete. The interior of a collapsed object in such a framework is not a smooth cavity of infinite density, but a compact region of saturated connections. This region may have properties unlike any known material. It might behave like a rigid lattice, a fluid of connections, or a hybrid structure that supports oscillations of geometry itself. These oscillations would ripple through the network, interacting with the horizon and contributing to the faint signals that escape over cosmic timescales. If detected, these signals would reveal the network's structure, offering direct evidence of the universe's deepest architecture. In alternative theories, the vacuum possesses hidden dimensions that compactify under high curvature. Collapse forces these dimensions to shrink or twist, creating new geometric configurations unavailable at lower densities. These compactified dimensions could absorb curvature that would otherwise create inconsistencies. Instead of allowing infinite compression, the universe routes the stress into these hidden channels, dispersing curvature across dimensions unseen by ordinary observers. In this view, the densest possible state corresponds to the full engagement of all dimensions, each bearing a portion of the burden. Such possibilities open the door to interpretations where collapsed regions act as gateways to higher dimensional configurations. Their interiors may not be confined to familiar dimensionality, but expand into shapes impossible to visualize directly. The densest state becomes not a point, but an interface between dimensional layers, a region where the universe expresses its full geometric richness. These interfaces could be stable, metastable, or fluctuating, depending on the underlying laws governing dimensional behavior. Another line of inquiry considers the symmetries of spacetime. Symmetries dictate conservation laws, particle behavior, and the structure of interactions. Under extreme curvature, some symmetries may break while others emerge. These emergent symmetries could define the interior state of collapsed objects, enforcing new conservation rules. In this regime, density would be governed not by mass alone, but by the representation of these symmetries within the geometry. The densest configuration becomes one that respects all preserved symmetries while integrating those newly formed under collapse. In a universe governed by such principles, collapse becomes a symmetry-driven transformation. Matter approaching its limit triggers shifts in symmetry, realigning the structure of spacetime. These shifts determine whether the interior stabilizes, fragments, expands, or folds into configurations beyond conventional description. Density's bound is then defined by the point at which no further symmetry changes are possible without violating the consistency of physical law. It is a conceptual horizon as much as a physical one. As research advances, more attention turns to how information behaves at these extremes. Information cannot be destroyed, yet a collapse seems to swallow it beyond recovery. But if density's upper bound is shaped by symmetries, vacuum structure, and network connections, then information must persist in these underlying layers. It may become encoded in the arrangement of connections, the phases of fields, the topologies of hidden dimensions, or the pattern of emergent symmetries. Retrieving this information may be impossible, but its existence reinforces that the densest state is not one of erasure, but of reorganization. This reorganization underscores a final insight. The densest possible condition of matter is not an annihilation of structure, but the fullest expression of the universe's rules. At the threshold of collapse, all physical principles converge, shaping geometry into a configuration where nothing more can be added, removed, or compressed without contradiction. Beyond this threshold lies no physical realm, only further abstraction awaits. And yet, this abstract boundary is woven into everyday reality. It shapes the orbits of stars, the formation of galaxies, the distribution of matter, the expansion of the cosmos, and the deep whisper of radiation that carries faint records of ancient collapse. The densest states of matter are rare, hidden, and silent, yet they define the outer limits of what the universe can be. The boundary of density becomes clearer when viewed through the lens of the research that has brushed against it. The Event Horizon Telescope provided humanity's first silhouette of a horizon, revealing a luminous ring formed by light orbiting the very edge of collapse. That ring was not a symbol, but a measurement, a direct imprint of geometry compressed to its limits. The research teams behind the image, drawing on observatories across continents, demonstrated that curvature itself can be photographed, that the densest states leave marks on the sky that technology can gather and interpret. In the realm of gravitational waves, detectors such as LIGO, Virgo, and Kagra have listened to the final spirals of merging compact objects. Their data capture brief vibrations in spacetime, each one tracing the structure of exotic matter before it vanished behind a newly forming horizon. These instruments showed that dense objects do not simply collide, they sing. Their final moments produce harmonics determined by the rigidity of matter, the tension of geometry, and the internal configuration that defines the approach to maximum density. After the collision, the horizon stabilizes and emits a final fading tone, a confirmation that geometry has reached the saturation point predicted by theoretical work from the decades following Oppenheimer, Snyder, and the later insights of Penrose. From space-based observatories like Chandra and XMM Newton, astronomers have watched the behavior of gas spiraling toward collapsed remnants. Their instruments detect emissions from heated plasma orbiting in the grip of extreme curvature. The patterns of flickering light reveal which regions of the disk are distorted by rotation, which are stretched by tidal forces, and which fall so close to the boundary that their light struggles to escape. The data confirm predictions from general relativity and also highlight discrepancies hinting at physics beyond the classical horizon. Some of the most delicate measurements come from NICER on the International Space Station, which maps the surfaces of neutron stars through their pulsations. NICER research groups have shown that the shapes of these stars are subtly warped by their internal pressures and rapid spins. These distortions reveal transitions in the material beneath their crusts, regions where the strong force begins to blur the distinction between nucleons and their constituents. Such observations guide theoretical work from institutes like Perimeter and Kavli, where researchers explore the boundary between nuclear structure and quark-dominated matter. Their calculations suggest that somewhere inside these compact stars, density approaches a regime where geometry itself begins to dictate the behavior of the constituent fields. Meanwhile, particle physicists at CERN, Brookhaven, and other laboratories recreate fleeting moments of extreme density through heavy ion collisions. The fireballs formed in these collisions display fluid-like behavior, an echo of the early universe when matter existed as a unified sea of quarks and gluons. Although these collisions last only brief instants, they reveal how matter behaves at densities approaching the quantum limit. They validate insights from theorists such as Shuryak and the lattice quantum chromodynamics community, who have spent decades mapping the behavior of matter in this domain. These experiments provide hints that, before collapse reaches the horizon, matter fully dissolves into a phase where geometry plays an intimate role in determining stability. Work in quantum gravity seeks to explain what happens after that point. Loop quantum gravity frameworks, explored by Rovelli and others, describe spacetime as a network of discrete connections. According to this perspective, collapse cannot proceed beyond the point where these connections saturate. Research from the Max Planck Institutes has examined how these minimal units of area and volume enforce a geometric floor. When density approaches this threshold, the collapse no longer tightens. It transforms. The interior behaves like a region of frozen geometry, unable to compress further because every fundamental connection has reached its maximum tension. String theory offers another interpretation. In programs led by researchers at Princeton, Harvard, and the Institute for Advanced Study, theorists explore the idea that collapsed regions funnel curvature into extended objects that cannot shrink indefinitely. These objects, vibrating elements of higher dimensional structure, absorb tension, redirecting collapse through channels hidden from ordinary perception. In this view, the densest state is not a geometric endpoint, but a transition into a richer configuration where extra dimensions participate in the redistribution of curvature. The holographic principle, refined by T. Hooft and elaborated by Maldacena, adds another dimension to the discussion. It proposes that every bit of information about matter falling inward is preserved not in the interior, but on the horizon itself. Research groups around the world have explored the mathematical structure of such horizons, treating them as surfaces with their own dynamics. In this framework, density's upper limit emerges as a boundary in information theory. No region of spacetime can encode more structure than its surface allows. The densest state is then defined not by mass or curvature, but by the capacity of a horizon to store and process information. Anticipating the implications of these ideas, some researchers at institutions like the Black Hole Initiative have proposed that the interior may not contain a singular core at all. Instead, it could hold a region where geometry oscillates around a stable configuration. These oscillations would never escape the horizon, but they would influence the final stages of collapse and the slow evaporation that follows. Over immense spans of time, these oscillations might imprint patterns on the escaping radiation, allowing a subtle echo of the interior to reach the universe outside. Meanwhile, research involving IceCube in Antarctica seeks to detect neutrinos from compact objects. Neutrinos can carry information from regions where photons cannot survive. Their behavior in the presence of extreme curvature may reveal transitions within the dense states that matter undergoes before crossing the horizon. Neutrino astronomy may become one of the few tools capable of probing the boundary between nuclear structure and geometric saturation, offering a glimpse into processes that unfold at the brink of collapse. Work at ALMA, studying molecules and dust near galactic centers, has shown how dense environments sculpt the dynamics of gas on scales vastly larger than the horizon itself. Patterns of rotation observed through ALMA data reveal the influence of compact cores whose densities exceed all ordinary limits. ALMA's precise measurements help distinguish between matter orbiting under classical gravity and matter orbiting in regions where relativistic effects dominate. These observations confirm predictions drawn from the early work of Wheeler and the later refinements by Thorne, demonstrating that the densest states exert influence far beyond their hidden interiors. At the theoretical frontier, researchers continue exploring how density influences the vacuum itself. Studies in quantum field theory and emergent spacetime models suggest that high curvature induces changes in vacuum fluctuations, altering the very foundation from which particles arise. This research spans multiple institutions, from the University of Tokyo to Stanford's gravitation groups, each proposing mechanisms by which the vacuum reorganizes under the stress of approaching the density limit. These models frame the densest state as an interplay between the vacuum's structure and the geometry imposed by collapse. In cosmological research, insights from the early universe continue to reshape thinking about density's upper bound. Findings from the Planck satellite revealed patterns in the cosmic background that echo conditions of extraordinary compression. These findings align with inflationary models developed by Guth, Lind, and others, which describe the universe's earliest moments as a phase where density approached its conceptual limits before expanding into the form we see today. Understanding these early processes informs theories of collapse at the other extreme, highlighting asymmetry in the universe's behavior under extreme compression and extreme expansion. Finally, ongoing work investigates how density limits might influence the future of cosmic evolution. Some researchers propose that evaporating collapsed objects contribute to the accelerated expansion of the universe by releasing energy into the cosmic medium. Others speculate that the eventual dilution of matter will leave behind only the faint radiation produced by once dense regions, allowing the universe to transition into a state where geometry becomes increasingly uniform. In this distant future, the densest states of the past will have left only their whispers embedded in spacetime. In every strand of research, from telescopes capturing the silhouette of horizons to colliders recreating primordial matter, from gravitational wave observatories listening to the last vibrations of collapsing stars, to quantum theorists mapping the boundaries of geometry, one message emerges with clarity. The universe enforces a limit on density through the union of its deepest rules. This limit is not a wall but a convergence, a place where matter, information, and geometry merge. The densest possible state expresses the essence of physical law, a state where nothing more can be added without redefining the universe itself. Across the quiet reaches of the universe, there are signs that the densest states influence phenomena far removed from their own formation. Cosmic rays, for example, drift in from intergalactic space carrying energies that hint at origins near collapsed objects. Yet their precise pathways remain blurred by magnetic fields. The research tracing these trajectories suggests that regions of extreme curvature act not only as absorbers of matter, but as accelerators, flinging particles across cosmic distances long after the internal state has settled into equilibrium. These particles traverse the void as mute reminders that collapse does not silence energy, it reconfigures it. The same influence appears in the behavior of gas clouds drifting through galaxies. Their motions reflect minute imbalances in gravitational potential shaped by hidden dense remnants scattered throughout stellar populations. Some of these remnants reveal themselves through faint emissions, captured by observatories that track the smallest fluctuations in starlight. Others remain completely dark, detectable only through their pull on surrounding material. This interplay between visibility and invisibility reinforces that density's limit produces objects whose significance extends far beyond their detectability. In certain galactic cores, patterns in stellar movement indicate that the central mass possesses an influence exceeding that of ordinary stars. Observations have shown stars looping around an unseen source in elegant arcs, their paths bending through geometric conditions that match predictions from the first serious mathematical treatments of collapse. These observations, carried out over decades, provide some of the clearest natural experiments for understanding how curvature behaves when pushed near its extremes. Each orbit, each precession, Each unexpected turn strengthens the case that density's upper limit expresses itself not only in hidden interiors, but in the choreography of visible matter. In quieter regions, the relic radiation permeating the universe carries faint irregularities that researchers continue to unravel. These irregularities reflect both expansion and compression on cosmic scales, influenced by dense structures that formed long after the earliest moments. The patterns are subtle, like faint ripples in an immense ocean, but they contain insights into how dense regions shaped the distribution of matter long before galaxies matured. Research groups studying these fluctuations often find correlations that point to the gravitational footprint of collapsed objects, even when their interiors remain sealed behind horizons. The ongoing effort to simulate collapse on supercomputers provides another glimpse into density's upper bound. These simulations, run across vast networks of processors, demonstrate how matter transitions through stages of compression until geometry takes over entirely. While each model depends on assumptions about the nature of quantum gravity, they share a common conclusion. Collapse funnels matter into a regime where no conventional force can describe the behavior. The simulations evolve further only by invoking principles drawn from theoretical frameworks that treat spacetime as something deeper than a smooth continuum. The resulting patterns, though mathematical abstractions, hint at internal architectures shaped not by material pressure, but by the organizing constraints of geometry itself. Subtle connections continue to emerge between these theoretical models and phenomena observed at a distance. Occasionally, the fading afterglow of a cosmic merger displays features that do not align with classic expectations. These anomalies suggest internal processes unfolding beneath the horizon that subtly shape the final emission. Researchers exploring these signals find echoes of the principles laid out in early theoretical work on trapped surfaces and dynamic horizons. Observations that indicate that collapse is not a single action, but a sequence of adjustments, each governed by the interplay between matter, energy, and geometry. There are also indications that the densest states may influence the structure of time itself in their vicinity. Certain models describe regions near the horizon where temporal flow becomes multi-layered, allowing different slices of spacetime to coexist with varying rates of progression. While this can't be observed directly, its consequences make their way into the timing of pulsations from nearby stellar remnants and into the modulations of light streaming past horizon boundaries. These subtle signatures help refine theories that once relied solely on mathematical symmetry, linking them instead to observations collected through increasingly sensitive instruments. Another surprising consequence of density's upper bound appears when examining how matter responds as it approaches collapse but does not quite reach the horizon. Some stars in their late stages compress into forms that resist complete collapse through exotic arrangements of their internal components. These arrangements may involve mixtures of nuclear phases and quark-like fluids, each contributing to the pressure that holds collapse at bay. Although such states lack the absolute finality of horizon formation, they skirt the limit closely enough that their study offers a natural laboratory for understanding the transition between matter and geometry. Observations of their thermal emissions and oscillations complement laboratory research on dense phases of nuclear matter, revealing a continuity between astrophysical extremes and terrestrial experimentation. In the study of active galaxies, researchers have found that jets launching from dense central regions often display structured patterns suggesting that magnetic fields and curvature collaborate to focus the outflow. These structures do not emerge in simulations that ignore the deeper geometry of collapse. Only when the models incorporate the curvature near the threshold does the jet maintain coherence over incredible distances. This connection reinforces that density's limit shapes phenomena far beyond the horizon, influencing the behavior of matter and fields across intergalactic space. There are also investigations into how density affects the long-term evolution of star clusters orbiting central collapsed objects. Over extended timescales, the motions of these clusters reveal the slow reshaping of the gravitational environment, as the object at the core subtly changes through processes predicted by quantum theories of evaporation. Although extremely slow, these changes accumulate, eventually altering the cluster's structure in ways that match predictions from theories that treat the boundary as a dynamic surface with its own degrees of freedom. The agreement between long-term motion and theoretical expectation strengthens the idea that collapse culminates not in an immutable point, but in an evolving horizon. In cosmic voids, vast regions nearly empty of galaxies, the influence of dense states might seem absent. Yet even here, faint distortions in the distribution of hydrogen reveal tidal remnants from distant collapsed objects. These distortions whisper of past events, perhaps mergers or disruptions, whose gravitational influence propagated outward long after the visible signs faded. By studying these faint signals, researchers gain insight into how curvature travels through the universe, distributing the influence of density even into the most isolated regions. The more these threads are studied, the more apparent it becomes that the universe has woven density's limit into every level of its structure. Collapsed objects shape galaxies. Dense remnants guide star formation. The earliest cosmic fluctuations bear the imprint of states that brushed against the boundary. Even the vacuum responds to the presence of curvature by rearranging its fluctuations, suggesting that the universe has built its own safeguards into the fabric to prevent contradictions. Through all of this, the interior limit remains sealed. The densest state exists beyond full comprehension, yet everything surrounding it reflects its nature. The horizon behaves like a mediator, translating the inaccessible into patterns that distant observers can study. Each observation, whether of light bending around a collapsed core or waves trembling through space-time, hints at the structure of a region where matter has lost its identity entirely. The deeper the research goes, the clearer it becomes that density is not merely a quantity to be measured, but a gateway to understanding the architecture of existence. The limit is not defined by the crushing of particles, but by the moment when geometry itself becomes the only remaining substance. A state where the universe's rules reach their full expression and no further compression is possible without rewriting the laws themselves. The boundary of density communicates itself not only through astrophysical observations, but through the delicate behavior of systems that appear unrelated at first glance. In certain laboratories, ultra-cold matter is coaxed into regimes where quantum effects dominate completely, allowing researchers to witness transitions that echo those believed to occur in dense astrophysical interiors. The patterns formed in these controlled environments, though vastly less extreme, reveal symmetries that mirror predictions about how matter rearranges itself when pushed toward its ultimate threshold. Even these modest experiments demonstrate the influence of the deeper rules that govern collapse. On planetary scales, density expresses itself in subtler ways. Some worlds possess interiors compressed enough to alter their magnetic fields and atmospheric behavior. The organization of these interiors reflects the balance between pressure and quantum forces, though nowhere near the brink reached inside collapsed remnants. Still, the correspondence is unmistakable. Compression reorganizes matter until it aligns with the geometry imposed upon it. This pattern repeats from terrestrial planets to massive gas worlds and onwards to stellar remnants, each step marking a deeper encounter with the relationship between matter and curvature. Within stellar populations, certain systems exhibit pulsations or flickering patterns that reveal internal transformations, aligned with theories of dense matter. These oscillations arise when pressure waves travel through layers that resist compression in different ways. Their timing and modulation carry the imprint of transitions both subtle and profound, including those leading toward the threshold where geometry takes primacy. While these signals are faint, researchers analyzing them uncover the fingerprints of physics that approach the limits without crossing them. In contrast, some astronomical environments push matter outward rather than inward. Stellar winds, supernovae, and energetic outbursts eject material across vast distances, dispersing it into diffuse clouds. These processes counterbalance collapse by redistributing mass and energy across the galaxy, ensuring that density remains a dynamic variable rather than a monotonic path. The balance between explosive release and gravitational compression creates the long-term rhythm of stellar evolution. Without the outward flows, galaxies would quickly collapse into structures dominated by dense remnants. Without inward pull, the cosmos would lack the variety of forms that arise from this interplay. Even on galactic scales, motion reflects a contest between forces that gather matter and those that diffuse it. Spiral arms form when density waves propagate through rotating disks, gathering stars and gas into arcs that persist across the ages. These waves show how density influences structure without requiring extreme compression. Their existence suggests that the universe contains gradients of density at every scale, each expressing a different layer of the governing architecture. Far beyond individual galaxies, clusters and filaments stretch through the cosmos, forming a web-like structure connecting distant realms. The density of matter in these filaments remains low compared to collapsed objects, yet the geometry they produce is unmistakably sculpted by the same fundamental principles. The filaments trace paths where gravity has steadily accumulated material over cosmic time, guiding it from diffuse beginnings toward ever more intricate configurations. At the intersections of these filaments, where clusters form, the influence of dense remnants becomes prominent, revealing how the upper limit of density exerts a quiet directive over the evolution of structure. Even the interstellar medium, seemingly calm and sparse, carries echoes of density's authority. Subtle temperature differences, magnetic alignments, and variations in ionization reflect historical encounters with regions of compression or radiation from collapsed remnants. In this sense, the densest objects broadcast their influence across volumes far larger than their physical presence, shaping gas clouds that may not encounter collapse for millions of years. Particles that travel through these regions, cosmic rays, neutrinos, high-energy photons, act as messengers from places where density briefly soared before dispersal. Their interactions with the medium reveal the trails left behind by ancient events, long faded yet still detectable to instruments sensitive enough to catch their faint signals. These particles represent the universe's memory of compression, carrying with them a record of density's influence long after the transient events that produced them have concluded. Yet the deepest expression of density appears not in matter or radiation, but in the structure of spacetime itself. The universe behaves like a medium capable of responding to tension, stretching gently across expansion and tightening in the presence of mass. When compression becomes extreme, spacetime does not fracture but reorients its structure, redirecting curvature into forms that preserve consistency. This flexibility ensures that collapse does not lead to contradictions, allowing dense states to exist without destroying the coherence of physical law. In the study of cosmological models, this flexibility becomes central. Some formulations depict the universe as evolving through stages where curvature intensifies and then relaxes, suggesting that density's upper bound has guided the cosmos not only in isolated collapse events, but in its broadest arcs of history. Researchers examining some early universe scenarios find patterns indicating that geometry once approached a saturation point before unfolding into the expansive domain now observed. These ideas remain speculative, but carry an internal logic consistent with the limits inferred from collapsed objects. In more recent theoretical work, certain researchers propose that the densest regions within the cosmos may also serve as seeds for future complexity. Although their interiors remain sealed from view, their horizons store information that may influence the long-term evolution of the universe. Evaporating remnants release radiation that, over unimaginable timescales, disperses into the cosmic medium. The distribution and structure of this radiation contribute to the gradual rebalancing of the universe as it drifts toward a more diffuse configuration. Density's upper limit, once reached, leaves behind a legacy not confined to the horizon itself, but dispersed across the vastness. Particular interest surrounds the question of whether dense remnants might influence the stability of the cosmic expansion. Some research suggests that the energy released during the slow evaporation of collapsed objects could subtly affect the balance between gravity and expansion. If this is true, then density's limit continues to shape the universe even after collapse has halted. The densest states become long-term participants in cosmic evolution, their influence lingering through the faintest radiation, escaping the boundaries of their horizons. This radiation itself carries subtle structures. Although its individual quanta appear random, their collective patterns may reflect the internal dynamics of the collapsed region. Some theoretical analyses propose correlations that could encode a form of the interior's history. While detecting such correlations remains beyond current practicality, the possibility underscores the idea that nothing inside a horizon is truly lost. It becomes reorganized into patterns that the universe gradually releases. Density's limit thus becomes a stage for transformation rather than finality. Interest has also grown in the possibility that dense remnants may interact with the vacuum at the deepest level, altering fluctuations in a way that subtly influences the local behavior of fields. This interaction may not produce noticeable effects in everyday environments, yet it could accumulate over immense time spans, contributing to changes in how energy is distributed across the cosmos. The vacuum responds to curvature through shifts that are small but consequential, shaping how the universe cools, expands, and stabilizes over eras far exceeding stellar lifetimes. These ideas converge on a single theme. The densest possible state is not merely a punctuation mark in the life of a star, but a reference point for the universe itself. It defines the maximum expression of compression that physical law permits, and in defining that limit, it shapes everything that happens at lesser scales. From the way matter aggregates in galaxies to how the cosmic background carries faint imprints of ancient structure. Density's upper bound serves as an invisible architect guiding the evolution of form. In the most speculative regions of research, some propose that the universe could contain rare configurations where geometry achieves densities near the limit without involving matter at all. These configurations might arise from the interference of gravitational waves or from exotic fields predicted in some theoretical models. If such structures exist, they would represent the purest expression of geometry near saturation, free from material influence. They would reveal how spacetime behaves when it confronts its own constraints, independent of the forces that ordinarily drive collapse. Though these structures remain hypothetical, their study reflects an expanding view of density as a property not restricted to material objects. Instead, density becomes a quality of geometry itself, a measure of how deeply spacetime can curve while still maintaining coherence. Collapsed objects represent one pathway to this limit, but the limit itself transcends matter, anchoring the universe's architecture in principles that apply everywhere. Across all research, from telescopic observations to gravitational wave detections, from laboratory experiments to speculative theories, one thread holds steady. The densest state is not a collapse into nothingness, but a transformation into the full expression of the universe's structure. It is where matter yields to geometry, where geometry yields to quantum rules, and where the fabric of existence arranges itself into its most concentrated form without surrendering to inconsistency. What emerges beyond that threshold is no longer governed by the language of mass or pressure. It becomes a domain of relationships between fields, between symmetries, between the fundamental units of space-time that define the limits of what the universe can sustain. And even though this domain remains hidden behind horizons or buried in the earliest cosmic epochs, its presence echoes across every level of structure, shaping the evolution of stars, galaxies, and the vast cosmic web. In the end, the question of how dense matter can become before space gives in leads into a realization that the limit is not the collapse of substance, but the completion of structure. It is the moment when the universe gathers every rule it has ever written into a single configuration, balancing them with a precision that allows nothing further. At that boundary, matter no longer falls inward. It transitions into a state where geometry carries everything that once defined it. The horizon becomes the surface of that transformation, a quiet veil where the deepest constraints of reality hold steady without strain. Every collapsed object, every hidden core, every echo of ancient compression shows that the universe never allows contradiction to form. Even where gravity tightens its grip, even where fields twist into unfamiliar shapes, the architecture remains coherent. The densest possible state becomes a testament to this coherence, a point where the cosmos reveals how far its laws will bend and where they choose to rest. And, as the universe stretches outward, carrying galaxies apart and cooling the radiance of ancient events, these densest states remain woven through the cosmic fabric, shaping motion, guiding structure, and whispering their influence into the background that surrounds everything. Their horizons mark places where questions pass beyond reach, leaving only the assurance that the underlying rules hold firm even in their most extreme expression. Thank you for exploring this with me. If this kind of journey into physics, cosmology, and the deep architecture of reality resonates with you, feel free to like the video and subscribe to the channel. There are many more frontiers waiting in the quiet spaces between stars, and I'd be glad to explore them with you.